So thanks a lot, Jayaram. Jayaram Chengalur is a professor and dean at the National Center for Radio Astrophysics, and his research focuses largely on extragalactic astronomy. He's interested particularly in studies of dwarf galaxies, neutral hydrogen absorption in high-redshift galaxies, from the so-called damped Lyman alpha systems, and in general studies of evolution of neutral hydrogen content of the universe. He's also interested in instrumentation, ISM, and evolution of fundamental constants, a very broad range of interests. In the first two lectures, he'll talk to us about interferometry, which Nissim just mentioned gives us much higher angular resolution than single-dish observations, and imaging, the stunning images that radio astronomers produce. And later in the school, he's also going to talk to us about neutral atomic hydrogen, where he has done a lot of interesting work on dwarf galaxies with the JMRT. Jayaram, please continue here. Thanks very much.
Yeah, thanks, Sakya, for that introduction. And so then probably without further ado, I'll start. I'm happy to take questions in between. So if you have something, anybody would like to ask, please go ahead and speak up. So Nissim just gave, quite a nice, but also very broad introduction to radio astronomy. And let me just pick a few things from there, which I'd like to sort of build on. And there are also some few things which I'd like to introduce, which Nissim didn't get around to saying today, but we'll probably talk about tomorrow. So the one thing which I guess, would be clear by now is that radio astronomy is basically observations of extraterrestrial objects at wavelengths in the radio regime, which is typically between of the order of a millimeter or a fraction of a millimeter to wavelengths of the order of 10 meters or so. And as you all saw, that is constrained by what is called the radio window of the Earth's atmosphere and ionosphere. These are the only wavelengths which, from sources outside of the Earth, which can penetrate the atmosphere and ionosphere and reach the Earth. And of course, it's a large wavelength range. It's almost a factor of 10 to the power of 4 in wavelength. And so, the technologies that we will use to detect these waves will vary quite dramatically when you go from one wavelength regime to another wavelength regime, which is 10,000 times bigger wavelengths. But nonetheless, there's still a lot of broad similarity in the way in which these signals are processed. And Nissim spoke about the similarity as far as, detecting sources with one single parabolic reflector is concerned. And I'd just like to pick up and remind you of a little bit of what he said a few minutes ago. That is, supposing I have a reflector telescope, and for simplicity, let's assume that it's parabolic. It's a parabolic reflector, and that it has a diameter d. You'll have to bear with my writing, because I am not that used to writing on a pad, but I hope it's legible, right? So what happens if I have a parabolic reflector like this is that rays which come in parallel to the axis of the reflector will reflect off the reflector and go to the focus. Okay. So this is what happens. So I have some very distant source, which I can regard as unresolved. So it's a point-like source. So the light coming from it, since it's very far away, consists of parallel rays, a plane wavefront. And those rays of light, when they strike the reflector, all of them will come and end up at the focus. So what we can then do is to put a small receiving antenna at the focus. And this antenna will take the radio wave and convert it into a voltage, and that voltage will be further processed. And we will do all of our analysis on the voltage that this antenna produces. So this antenna at the focus is called a feed antenna. And Nissim spoke about a number of arrangements, different arrangements for the reflector. And one of the things which he did mention was what was called the resolution of this system. So if I had an infinitely large parabolic reflector, then what would happen is that the things which arrive at the focus would only be the rays which are coming parallel to the axis. But since the reflector has a finite size, which is d, there will be diffraction effects. And so therefore, this antenna will receive rays not only from those which come parallel to the axis, but it'll also receive some energy from rays which are at a slight angle to the axis of the parabola. And in general, Nissim showed you the sensitivity pattern as a function of angle, that I'll have something like this, that I'll have, this is sensitivity as a function of direction. So I get maximum sensitivity along this direction, which is the axis of the parabola, but I also have sensitivity along other directions. And there might also be some secondary maxima, much smaller than this, hopefully, in other directions. But the bulk of my sensitivity is in that direction along the axis of the parabola. And the half at the angle at which the sensitivity falls to half, which we could call theta 0, would be the resolution. So, and he also said that theta 0 goes roughly like the wavelength divided by the diameter. Right? So that means that if I'm looking in a particular direction, I've pointed my radio telescope in a particular direction, and I see some radiation, I'm not very sure where exactly the radiation has come from. It could have come from anywhere within this angle, right? Because my telescope, roughly speaking, is sensitive to radiation in that range of directions. So this theta 0 then would be the resolution of the telescope. But there's another way I'd like to look at the same thing, which is that this telescope is not sensitive to sources which lie, roughly speaking, outside of theta 0. Supposing I had a radio source which was well removed from the axis, which was at a distance, angular distance from the axis, much larger than theta 0, then I would receive no radiation from that source. So another way of looking at this is to say that this angle theta 0 tells me the field of view of this telescope. So this is the only region of the sky that the radio telescope sees. Obviously, there are radio sources all over the sky, but the telescope, as far as the telescope is concerned, they might as well not exist because you don't pick up any radiation from them. The other thing which I'd like to say about this telescope, which I think Nissim also mentioned, was what is called the sensitivity. So the sensitivity depends on many factors, but one of the things it will depend upon is how much energy I'm able to collect from the source. And the amount of energy I'm able to collect from the source will obviously depend on the area of the reflector, because that's the only part of the wavefront which goes to the feed antenna. So it'll be proportional to the area, which goes like the diameter square. Right? So both the resolution and the sensitivity will improve as you go to larger and larger radio telescopes. But the sensitivity actually also depends on other factors, which Nissim will get into tomorrow. And so those factors, but I would like to say what they are. Those factors are the following, and they, you probably would agree that they are, one could, I think it's easy to appreciate that it would depend on these factors. So one of these factors is just the exposure time, or what in radio astronomy is called the integration time. The longer and longer I look at in a particular direction, the more sensitive one is to radiation from that direction. Right? So if I stare for a long time and I integrate the data for a long time, it's like increasing the exposure time in a camera. You begin to see fainter and fainter objects. And the other factor that it depends upon, and that presumably those details Nissim will get into tomorrow, is the bandwidth of the observation. That is, radio telescopes don't work at just one wavelength. They work at a range of wavelengths, as Nissim was highlighting. And so the larger the range of wavelengths, or the larger the frequency range over which you're collecting area energy, the more sensitive your telescope is going to be. So the sensitivity also depends on what would be called the bandwidth, delta nu, and the integration time, tau. And the dependence is a square root dependence. Right? So if I want to have a more sensitive telescope, I want to have as large a bandwidth as possible and as large an integration time as possible. So I'll pause here for questions, partly because I'm not sure that people are hearing me properly. So I'll just pause and just wait. Maybe you could, if you have anything to ask, please do. But maybe you could also just let me know that you're able to hear me properly.
Sir, can you please explain again the dependence of sensitivity on the bandwidth of telescope?
Yeah, so I won't actually attempt to explain it. Nissim, it'll take me too long. Nissim will get into these details tomorrow. But broadly speaking, you could understand that the wider the bandwidth, the more energy I'm going to collect. Right? I'm collecting energy not only at one frequency, I'm collecting it at a range of frequencies. And so the wider the range of frequencies over which I'm able to collect energy, the more sensitive I'm going to be. Does that make at least some intuitive sense?
Yes, sir.
What's integration time?
The integration time you could regard as the integration time is the amount of time I have looked at the source. I've collected data from the source for that amount of time. It's like the exposure time in a camera, but I'm not sure that analogy works very well, because I think these days in smartphones, you don't set anything. But you could imagine that supposing I were to collect data for longer and longer and longer, and I average it for longer and longer and longer time, I get more and more sensitive. It's the same way. I mean, I've collected energy for a longer period of time. So I have, you know, I'm more sensitive to faint sources, because that emits a little bit of energy per unit time. But if I've collected that energy for a long amount of time, I've got quite a reasonable amount of energy, I should be able to detect it. Yeah, sorry. Was there something else?
The same as radiation pattern, because I have heard the term radiation pattern, but not sensitivity pattern.
Yeah, so the radiation pattern and the sensitivity pattern are basically the same thing. The difference only is the context. When you think of the antenna as radiating a signal, as for example, if you were transmitting for a radar or whatever else, that pattern is generally called a radiation pattern. But if you're using it for receiving, then it would be a sensitivity pattern or a reception pattern. But these two patterns are exactly the same. They're identical patterns. An antenna which radiates efficiently in one direction also receives sensitively efficiently from that same direction. All right, so let me move on then. And so now let us suppose I want to, you know, Nissim gave you some numbers, but I'd like to just work through that again. Let's suppose I have a telescope whose diameter is of the order of 100 meters. And I'm observing at a radio wavelength, which is of the order of 20 centimeters. Right. So what would my angular resolution be? It would be of this order, which is 20 centimeters. So that's 20 into 10 to the minus 2 meters divided by 100 meters. And that is in radians. And so if I want it in degrees, I would just multiply it by 60, which is, you know, roughly, there are 57 degrees per radian, which I have approximated as 60. So can somebody tell me what that number turns out to be?
0.12.
0.12. It turns out to be 0.12 degree, or of the order of, let's say, 10 arc minutes. Something of that order, not exactly, right? Whereas what is the typical angular resolution in optical telescopes on the ground? There's Nissim mentioned that number, but some of you may know it from before.
Milliarc seconds.
Milliarc second is, yes, that is, you do get optical telescopes of milliarc second resolutions, but typically these are telescopes in space. On the Earth, there's a limit set by the turbulence in the atmosphere. Does anyone know roughly what that is? So, okay, doesn't matter. On the Earth, it's of the order of 1 arc second. Because of turbulence in the atmosphere, it's difficult at optical wavelengths to achieve unless you take special care about trying to nullify the turbulence effects in some ways. It's difficult to get resolutions better than about an arc second. Right, and you also know that there are, maybe you've heard or seen, and as you mentioned it also, radio telescopes which give you extremely high angular resolution. They give you angular resolutions which are adequate for one to image the shadows cast by black holes. That's what they call them, right? These black hole shadows, the Event Horizon Telescope, and so on and so forth. And so, you are able to achieve angular resolutions much, much better than an arc second. And so that's the sort of thing I'd like to talk about today. But first, let's just say that supposing I were to take the same approach to improving my angular resolution, and I build a parabolic reflector, even if I wanted to have a parabolic reflector which gave me 1 arc second resolution, that would correspond to diameters of the order of, a few hundred kilometers. And already just to get to a 1 arc second resolution, you can see that we are talking about completely, impractical sizes of telescopes. And I just wanted to show you a few things, because it's one thing to write these numbers down, but sometimes pictures help you get the idea better. So let me just try and share my PowerPoint. Okay, so let me skip over all of these. This is stuff that we spoke about. So this is what I said. A really large radio telescope have a resolution of about a few arc minutes, whereas optical telescopes have resolutions of the order of arc seconds. And to give you an idea of what things look like when you have resolutions of few arc seconds as opposed to resolution of few arc minutes, I've just taken a photograph of the moon in the optical, which has, reasonable resolution. And I've just degraded it by smoothing it to a resolution of the order of a few arc minutes. So, this is it. On the right, you have, this optical image of the moon. On the left is what you see after you've degraded the resolution to of the order of few arc minutes. So you can see you've lost a huge amount of detail. I mean, the loss is actually, remarkable. And here I haven't actually quite done it to tens of arc minutes yet. It's still better than a few tens of arc, than 10 arc minutes on the left-hand figure. On the right-hand figure, you can see the craters. You can see all kinds of fine details on the surface of the moon, even though, we are not talking about very high optical resolution on the right side. On the left, you can just about say that you're looking at a roughly spherical object, and that on the bottom left corner, maybe it's a little brighter than it is elsewhere, that it may be a little bit darker towards the middle and towards the left. That's about all you can see on the left-hand figure, right? So you actually lose an enormous amount of information when your resolution has degraded to this extent. And so you really would like to have significantly higher angular resolution than would be afforded by telescopes of the diameters of the order of a few hundred meters. And again, to just give you a sense of scale, supposing I wanted an radio telescope operating at centimeter wavelengths to give me an angular resolution of the order of arc second, I've just superposed the diameter that you need on a map of Maharashtra, right? And you can see, what a significant fraction of, the area of that state would have to be covered with metal if you wanted to actually do this optical, this arc second kind of resolution radio telescope. That's obviously impossible, right? So, we have to think of some other way in which you would get a good angular resolution while working at wavelengths of the order of a few centimeters. All right, so as I was mentioned in that slide, the angular resolution, you get high angular resolution in the radio via interferometry. And so now what happens is that you take two radio telescopes and you separate them by some distance, and you receive the radio wave separately using these two telescopes, and you then sort of interfere them with one another. Right, and as you would know from your double slit experiments, at this point, what is relevant is really the separation between the two telescopes. That's the thing which sets whether you have constructive or destructive interference, or in effect, what sets the resolution of this thing, right? So you would see clearly the moment I've taken two separated antennas and I interfere the signals received at both of these antennas, the angular resolution that I would be dealing with would be set by the separation between the two antennas and not the size of the antennas themselves, right? So that's the way in which high angular resolution is obtained in the radio. And the separation can be very large. It could be of the order of, the size of the Earth. And you could go down to wavelengths, if you are willing to operate on mountaintops and so on, of the order of a millimeter or smaller. And so you can, as you would say, I leave it for you to calculate. You could achieve extremely high resolutions indeed. And it's indeed telescopes like this which make up the Event Horizon Telescope, which was used to make those very high angular resolution images around a black hole. So what we have
can you
then,
repeat what we were talking about, how to get high resolution in by radio interferometry?
Yeah, so we take two antennas and we put them at some distance from each other. Right, I have one antenna over here, another antenna over there, and I receive this array over here, I receive this one over there. They are separated by a distance x. And I take the signal from this antenna, I take the signal from this antenna, and I will multiply them together. Okay, it's a little bit like your double slit experiment, right? What happened in your double slit experiment? You had a coherent source of light, which came in through slits here and here. And then what did you do? You had a screen at some distance over here. And at different points in the screen, you just asked the question, what is the difference in path lengths between these two sources? And if that difference in path length was n lambda, you had constructive interference. And if it was some fraction of lambda by 2, then you had destructive interference. That's correct, right?
Yes, sir.
And what did that, whether the path length difference itself depended on the, you can see from the geometry, it depends on the separation of the two slits. It doesn't depend on the size of the slits. Right? That was the relevant number when you did these, when you did all of these. This was the parameter which set where constructive and destructive interference would happen. And the same way over here, you can see that there was a path length difference between these two rays. The ray over here will reach earlier than the ray over there. This ray has to travel this extra distance, right? And so if I multiply those two signals together, they'll basically interfere. Sometimes they will be in phase, sometimes they will be out of phase. Does that make things a little clearer?
Yes, sir.
And you will see that the whether I'll get things in phase or out of phase will depend on x and not the size of each one of these, which we assume is small compared to x.
Yes, sir.
Yeah. Okay. So, but now, you know, I did say double slit experiment, but there are actually important differences between the double slit experiment and what we are doing here. One, you would have already seen as I was speaking, that in the double slit experiment, actually what happens, you add these two waves together, right? There's a wave coming from here, there's a wave coming from here, and you add their amplitudes and you see whether they add in phase or they add out of phase and whether there's constructive or destructive interference. Here, what is happening is that we are doing a multiplication. We take this signal, we take this signal, and we multiply them together. Actually, we also do a further operation, which is to average them for some time, which I'll just show as a kind of integration. And that's what's called as a correlator. And that's for an important reason, which I'm going to come to in a moment, that this kind of operation allows you to make an image of the sky. So that is the second difference between our apparatus and the double slit experiment. In the double slit experiment, we had a coherent source, right? You have these two slits, but the two slits are fed by a single coherent source, so that the light coming here is coherent with the light coming from here. Right? Whereas in our experiment, what we have is the radio sky. And the radio sky consists of very large number of sources. It's not just one source. So we'll have a large number of sources. We are not going to be dealing with one source. And what we are interested is imaging the sky to find out, for example, if these were, we can imagine them, let's suppose they're star-like objects, and so they're little dots on the sky. What we want to do is to image the sky to figure out where each one of our dots is, where the radio stars are, right? We want to make an image of the sky showing the location of all of these radio stars, assuming that they are star-like objects.
Sir, is there any reason for multiplying the signal?
Yes. So the reason for multiplying the signal instead of adding the signal, as I mentioned earlier, and I'm happy to do it again, we'll go through it in detail in a moment, is that I want to make an image of the sky. I don't have just one object. In the double slit experiment, I had only one source, right? I have one coherent source which feeds the light into these two slits. That's why the light in this slit is in phase with the light in that slit. They're coherent, as they call them. Right? There's no phase difference between the light in this slit and the light in that slit. All the phase difference happens only because of the propagation of the light between the slits and the screen. In our problem, we don't have a single source. I have many, many sources in the sky. And what I want to do is to image the sky. I want to make an image of the sky. And as I was saying, it's as though we could imagine for the moment that we have point-like objects, that they are like radio stars. What I want to do is to make an image which shows me the location of each and every radio star within my field of view. And to do that, as we will see, this particular operation I showed you on the left, where we multiply and average, is the operation which will actually allow us to do that.
Excuse me, sir. You said that the path difference will depend only on X, but it will also depend on the angle of incidence.
Absolutely. But what I meant was that it doesn't depend on the size of the slit, assuming that that size is small.
Okay, sir.
Right. I just meant because earlier we were seeing that the resolution depended on the size of the telescope. So the point I wanted to make was here that size doesn't matter anymore. That size only for as far as the resolution is concerned, it's only the separation between the two antennas which matters. You're right. The resolution will depend on other things also. It'll depend on the wavelength. It'll depend on the angle. All these things.
Okay.
All right. So there were two differences which we already highlighted between the double slit experiment and this. One, we are going to deal with more than one source. The second is, so we want to actually make an image of the sky. The second is that we're going to do this different operation which was related. I'm going to multiply instead of integrate. And the third is that I'm going to do this operation not at one wavelength, because as we saw, if I want good sensitivity, I need to observe over a range of wavelengths. So I'm going to do this operation over a range of wavelengths. Right? So these are the three differences which we need to bear in mind as we go along. So let me just start afresh and, let's just work through the mathematics of this a little bit. So I have these two antennas over here on the ground, 1 and 2. They're at a separation of, let's say, a distance x. And let's say they are looking at a source at some angle θ0 from the vertical, right? And let's suppose it's a very distant source, and so the rays are parallel, and that source has a intensity of I0. Let me call this antenna 1. Let me call this antenna 2. And as we saw, the rays will reach antenna 1 first, and after a while, because they have to travel this extra distance, so after a while, they reach antenna 2. And this extra distance, you can easily compute, is going to be x0 sine x sine θ0. So if the wavefront reaches antenna 1 at some time, it reaches antenna 2 at a later time, which we'll call the geometric delay. And that will be given by x sine θ0 divided by c. Right? And that will be called the geometric delay. That's the jargon. So if I write, so I have a sinusoidal wave, let us assume, at a frequency nu, and I'll write it out in phasor form, which I assume you're familiar with, that rather than writing it as sine 2 pi nu t, I will write it as e raised to the power of minus I 2 pi nu t, where I is square root of minus 1. I'm sure you're all familiar with this notation. And when we want to deal with the signal itself, we'll finally take the real part of all of this when we are done with all our operations. So I will have that V1 will be equal to e raised to the power of minus. You'll have to excuse me because I'm used to writing j instead of I. So I'll just write j because otherwise by habit in the middle of my thing, I will switch to j. So j is basically square root of minus 1. Sorry, I beg your pardon. So this is the signal at antenna 1. At antenna 2, the signal reaches, I'm sorry, I have to add one more thing over here. Right? Because we are dealing with the source of intensity I, its amplitude will be square root of this intensity I naught, its amplitude is square root of I naught. And at V2, I will have the same thing.
Sir, what are these V1 and V2?
Just hang on. I'll tell you. It's hard for me to write and talk at the same time. Still learning all these things. Okay, so this, thank you for asking that question. So you remember when I showed you a single dish radio telescope, I said that what happens is that the radio wave hits the parabolic reflector, gets reflected, goes onto the focus, and over there I'll put a small antenna which will convert the radio energy into an electrical voltage, right?
Yes.
You remember that. So this is the electrical voltage coming out. V1 and V2 are the electrical voltages coming out of the antennas.
Okay, sir.
Right? And because I'm dealing with a radio wave of frequency nu, these electrical voltages are also oscillating with that frequency nu. Right? So you're with me now, right? So what I do now, yeah, good, thanks. So what I do now is that operation of multiplication. And actually what we do is a little more complicated. I will multiply not V1 and V2, I will multiply V1 and V2 complex conjugate. Right, that's the actual operation that we do. And when I multiply the complex conjugates, you will see that the two square roots of I0 will become just I0. And I'll get e raised to the power of minus j 2 pi nu t into e raised to the power of j So this is the output of that apparatus that we were talking about. The apparatus which will take the voltages, multiply the complex conjugate of one with the other, and average for a while. This is what we get out, and we could call that, for example, this is the jargon. It's called a visibility. So the visibility due to the source at that angle θ0 will be I0 e raised to the power of minus j 2 pi nu tau g0.
Sir, in the diagram, does I naught represent the source?
Intensity. It is the intensity of the source.
Okay.
Right, and the amplitude will be proportional to the square root of the intensity. That's why I put a square root in the voltages.
Yes, sir.
Right, so now supposing I have not one source, but I have many sources, right? I have one source which has intensity I naught and it is at the angle theta naught, or equivalently has a geometric delay tau g naught. Then I have another source which has an intensity I1, which is at an angle θ1, or basically I could also call it a geometric delay tau g1, also, and so on until n sources. And let's supposing all of these sources are independent, so they're not going to interfere with one another, right? Then obviously the output of my apparatus will be V, which will be V0 plus V1 plus and so on up to Vn, right? Which will be summation over n In e raised to the power of minus j. You're with me so far?
Sir, can you explain the phase difference of x sine theta naught which we got?
Yeah. So I assume you're referring to this diagram. So I have a source which is at this angle theta naught, right? It's very, very far away. So I regard the rays as coming from the source as parallel. Right?
Yes.
Parallel rays coming from the source, they strike antenna 1 and they strike antenna 2. Right?
Yes, sir.
And it'll reach antenna 1, that wave front will reach antenna 1 before it reaches antenna 2, because the ray has to travel this extra distance to reach antenna 2, correct?
Yes, sir. Yes, sir.
So that means that supposing I have a maxima at some point over here, at that time I won't have a maxima at 2. I'll have a maxima after that wavefront has traveled from here to here. Only after that much time I will have a maxima at 2, correct?
Yes, sir.
Now this distance is x sine θ0. Agreed?
Yeah, yes, sir.
And so the time it takes for the light to the radio waves travel at light speed for the radio wave to go from there to there is x sine θ0 divided by c.
Yes, sir. Got it.
Yeah, so there's a phase difference of nu times tau g0 between these two waves. Between the voltage here and the voltage there, we'll have a phase difference of the frequency times tau g0. Right? You probably are normally you all may think of it, you'll think if you're thinking in terms of path lengths, hang on, let me just find my cursor. So you would probably think of it as a path length where the phase difference would be given by x sine θ0 divided by lambda. But since mu lambda is equal to c, right, that phase difference would also be x sine θ0 divided by c into mu, right? Instead of dividing it by lambda, I can multiply by nu and divide by c. It's the same thing. It still gives me the phase difference. Right? Okay?
Yes, sir.
Sir, I have one doubt.
Yeah.
Sir, these I0, I1, I2 and are different sources.
Yes.
So, sir, are
They're
they all
independent.
at same frequency?
They're all emitting at the same frequency, but they are independent.
Okay.
The phases are not they're not locked together.
Okay, okay, sir. So is this a basic model? Because I once remember you said that we consider many wavelengths.
Yes, yes. So this is yeah, that's a good question, and that indeed was where I wanted to go next. We need to consider many wavelengths. So we've set up the zeroth order model. This is what happens if I had only one wavelength. What is going to happen if I had many wavelengths, right? So let's look at that next. And to do that, I want to just make the problem a little bit simpler. Let's suppose there's only one source at 2. Suppose just one source. Right? Then you know that this thing over here is the output that I would get from my apparatus, which by the way is called a correlator, right? That complex multiplication and averaging is called correlation, right? So this is the output that I get from my correlator for a single frequency. So now I want to know what is going to happen if instead of one frequency, I observe over a range of frequencies, right? So let us suppose we are observing over a range of frequencies between mu0 minus delta nu by 2. I observe over all these frequencies. That is basically, I will average the power over all these frequencies. So I could call that thing V bar if I want. It'll be the average power over all of these. Right, which is easy to work out.
Sir, won't we get a negative sign 1 by minus j 2 pi tau g naught?
Yeah. Thank you. So you could see that the delta nu term will come out in common, e raised to the power of j 2 pi nu. Sorry, I have to put a nu naught. Let me just get my cursor again. And I have to put a tau g or naught over here. Tau g naught, right? So the term involving nu naught will come out in common, and the term which remains will basically be the sine function, right? And so it will not surprise you that this turns out to be, and I'm not worrying too much about the signs. right? This is what happens. So if instead of observing over a single wavelength, I observe over a range of wavelengths, what I get is these two terms. The first term you will recognize, this is the same that we had before, right? This was the output when I observed only a single. If I observed just a single wavelength, this is what I got. And so what I get, the first term is exactly that same term at the central frequency nu naught. So I get that first term at the central frequency nu naught. The only problem is that it's multiplied by this additional term, the sine pi delta tau g0 divided by pi delta tau g0, which is basically sine x by x. Does anyone know what that function is called? It's a well-known function. What is that called? It's called a sinc function, right? So it's sine x by x, which is a sinc function. And this is what the sinc function looks like. It is maximum with the value of unity at the center, and then it very rapidly, it oscillates, but it very rapidly falls to zero as we go out. I haven't drawn it perfectly, but you get the general idea, right? So let's just take some typical values. Let's supposing that my delta nu is of the order of 10 megahertz, which actually is, as bandwidths go, relatively small. And let's supposing that my x, that is the separation between the antennas, is of the order of 30 kilometers, right? So then my delay, which will be of the order of x sine theta, we know, sine theta we take to be of order 1. So it'll be of the order of 30 kilometers divided by the speed of light, which is 3 into 10 to the power of 5 into 10 megahertz, which is 10 to the power of 7 hertz. Right? So it turns out to be of the order of 1,000, right? Unless I make a mistake. Right?
Yes.
Sir, is this tau g the time or the phase?
This is time.
Oh,
Sorry. Sorry. 10 to the, yeah, that's correct. It's the phase. I beg your pardon. It's the phase. You're right. I should call this the phase. Thank you. It's not tau g. It's tau g into nu, delta nu.
but sir, it should be time, right? Because nu
Delta nu, this delta, sorry, let me write this neatly. Just hang on. Delta nu into tau g is of this order. Why should it be time? This is time. X divided by c is time, and then I've multiplied it by delta nu, which is 10 to the 7.
Yes, sir.
Yeah, so it's phase. So basically, we are sitting here somewhere. We are sitting at 1,000 over here, right? And you know that this first minimum will happen basically at pi, right? So you're sitting many times past that first zero crossing. So you're sitting at a value where that sinc function is very close to zero. So even if I actually have a bandwidth which is just as small as 10 megahertz, which I was saying is a relatively small bandwidth, I have a problem that the output of my interferometer is basically zero. This correlator output has basically become zero, and that's not, so that doesn't help me. I need to have a wide bandwidth, otherwise I don't have sensitivity. But the moment I make my bandwidth wide, the signal fades away. Why is it fading away? It's fading away because if I get constructive interference at one frequency, at some other frequency, I will get destructive interference, right? Because the path length at one lambda may be, integer multiple of lambda. At some other wavelength, it would be such that the phases are pi out of phase and everything cancels. Right. So if I have a large enough bandwidth, I have as many frequencies at which things add up in phase as in which they cancel, and I get nothing. So if I want to have a reasonable signal, I have to be sitting somewhere here near the peak of this sinc function. So that means basically that I should be sitting very close to zero phase over there. So that I can do in two ways. I can do it in either I can say that tau g has to be close to zero, or delta nu has to be close to zero. By close to 0, maybe I should just say much less than 1. So either I have to work with very small tau g, or I have to work with very small bandwidth. I don't want to work with very small bandwidth, right? And so what I should do, therefore, is to find a way to make the geometric delay very close to 0. What was the formula for the geometric delay? Let's look at it again, right? The geometric delay was just depending on that path length difference, which went like x sine theta 0 divided by c. So if theta 0 is very close to 0, then I would have tau g very close to 0. I could use a large bandwidth and I would still get a reasonable signal. So that means if I take I'm just showing you one of my 2 radio telescopes, I'm actually now showing you the sensitivity pattern of this telescope. I point it vertically upwards. Then if I point it vertically upwards, it is sensitive only to radiation within the small region of the sky, right? Which I'll call delta theta now to avoid confusion, which would go like lambda by d of that telescope. So if I have the telescope and I point it vertically upwards, as we saw, it sees radiation only from a very, very small region of the sky, a region of the sky of the order of lambda by d. And so therefore, I will only have radio emission from that very small region of the sky. And over there, the geometric delay will be close to 0 because theta 0 is basically very close to 0. And I would be able to use a large bandwidth and get good sensitivity. Is that clear?
Sir, can you repeat that?
So I want to sit near the peak of this function, right? That much is clear to you?
Yes, sir.
So to do that, basically the argument has to be close to 0. It's sine x by x, right? This function is basically sine x by x. Right, where x is pi delta nu tau g 0. Right, so if I want to sit near the peak of this function, I need x close to 0, which means here either delta nu has to be close to 0 or tau g 0 has to be close to 0. Right, so that means one of the two of them has to be much smaller than 1. I want to use a large bandwidth because without a large bandwidth, I won't get sensitivity. So this option I don't want to take. So I want to take the option where the geometric delay between the two antennas is very close to 0. The geometric delay, the formula was sine x sine theta naught over c, where x is the separation between the two antennas. So if I'm looking vertically overhead, then the wavefront is going to hit both antennas at the same time, right? There's no delay, right? If I have these two antennas and they're looking vertically overhead, if this is the ray hits both antennas at the same time. There's no delay between them. So the geometric delay will be close to 0, and then I can use a large bandwidth. And how do I arrange that? I arrange that because I make my antenna point vertically overhead. And we saw that when we looked at a single dish radio telescope, it is sensitive only to emission at an angles which are of the order of lambda by d. It doesn't see any emission from sources outside this angle, right? So long as delta theta is much less than pi, then my condition is satisfied. Is that clearer?
Yes, sir.
Yeah. Okay. Sykes, just a minute. Sykes, are you there? Okay, maybe he's left.
I'm here, Jayaram, yeah.
Oh, yeah. Sorry, Sykes. I was just wondering, I might overflow by about 10 minutes or 10
Yeah, please carry on, actually. No worries at all.
Yeah, okay, thanks.
Yes, please do.
Yeah, sorry, there was another question.
Very nicely, and they're interacting, so it's wonderful, actually, to get the waves across. Please go ahead.
Yeah, thanks. Yeah, so go ahead. Yeah, please. There was another question.
So I was wondering if we could make the separation between the antennas smaller also, or is there some reason?
We could make the separation between the antennas smaller, but that kind of defeats the purpose because we wanted good angular resolution, right? And for that, I wanted a large separation because the angular resolution goes like lambda by x, where X is the separation between the two antennas. So I definitely want big X.
Okay.
Sir, so both our antennas will be pointing vertically overhead.
Both
all
are
the time?
antennas, that's correct. Both the antennas have to point vertically overhead because they have to see the same source.
Sir, but in that way, won't we be constraining our observations only to the sources which are vertically overhead?
Very good. Yeah. So we don't want to do that, but at least that's one way of doing that, right? If we agree that this would work, then we can see what to do for sources which are not vertically overhead.
Okay, okay.
Yeah. Okay, so let me go to that situation. Let's now suppose that I want to look at not vertically overhead, but I want to look at some angle like this, right? Which is, sorry.
Sir, I have this one doubt that they need not be exactly vertically overhead, right? They need to be on the something like the equator between the two antennas.
No, I'm not sure. But what are you saying?
Sir, like there will be some circle between the two antennas at which the source will be at the same
Yes. We are working in 1D right now, but so and in 1D we could just say it has to be vertically overhead.
Oh, okay, sir.
We'll extend to 2D in a bit. Okay, so now let's suppose I don't want to look just vertically overhead. We agreed that vertically overhead would work, but it's a pain because A, I can only look at a small part of the sky, and B, the sky sources rise and set, right? Because we are on a rotating Earth. So that means I'll see the source only for a very, very small period of time. If I want to integrate, if I want to have a large exposure time, it's very difficult for me to do that. So I don't want to do that. I'd prefer to be able to observe sources anywhere. Right, so now supposing I've pointed my antennas at theta 0, and again there will be this beam, right, at theta 0. So basically I'm going to see a part of the sky which will basically lie between theta 0 minus delta theta by 2 and theta 0 plus delta theta by 2. Right, this is the only area of the sky that I see. And so supposing in this area of the sky, I have a number of sources which are basically have intensity, I'll start with 1, which have I1 and lie at delta theta 1, or equivalently have geometric delay tau G1. And another source, which is intensity I2, lies at delta theta 2 and tau G2, and so on until I reach In delta theta n, or equivalently geometric delay delta tau Gn. Right? So I have all these sources in my field of view. And let me compute again what would be the visibility that I see. So first, let's just compute tau G1, right?
Sir, won't it be just tau Gn, or is it delta tau Gn?
Yeah, thank you. Yeah, so let's work out tau G1. Tau G1 will be x sine theta 0 plus delta theta 1 divided by c, which will be x by c into sine theta 0 cos delta theta 1 plus cos theta 0 sine delta theta 1. Right, and delta theta is 1, is all the delta thetas are much, much smaller than pi. So therefore, this term basically will be 1. The cos of delta theta 1 will basically be 1. And the sine of delta theta 1, I can approximate it as delta theta 1. So that will be x over c sine theta 0 plus x cos theta 0 divided by c delta theta 1, right, which was basically tau G 0 plus delta tau G1, where I've defined delta tau G1 as equal to x cos theta 0 delta theta 1 divided by C. Right? So now the total visibility that I get, which was, you will remember, it was summation over n, in e raised to the power of minus j 2 pi nu tau gn. I can write that as summation over n, in e raised to the power of minus j 2 pi nu tau g0 into e raised to the power of minus j 2 pi nu tau g1. Need another page. Okay, so this is what we have. And so if I, instead of dealing, since I know the direction in which I'm pointing, I know where I've pointed my telescopes. Therefore, I know tau G0 because I know theta 0, I pointed the telescopes over there. Right, so I can always multiply whatever I get with e raised to the power of j nu tau G0, which I could call V tilde. And then all of this would cancel out. It would basically become n e raised to the power of minus j 2 pi nu delta tau G1. I beg your pardon. I forgot this would have confused the hell out of you. This was delta tau G1, right? Let me just go back over here, right? I've worked out that tau G1 is basically tau G0 plus delta tau G1, where delta tau G1 is defined by this. And so therefore, in this summation where I have tau Gn, I replace it by tau G0 plus delta tau G1. And this factor, which is e raised to the power of minus j 2 pi nu tau G0, which is common for all the sources, right? It's the same for all all n sources. I take it out to the left, and I know that factor because I know where I have pointed the telescopes, right? So I will therefore get this relationship between my correlator output and the visibility. And so that basically, if I were to write out the expression for the differential delay, delta tau Gn would be the differential geometric delay, is e raised to the power of minus j 2 pi nu naught x cos theta 0 divided by c into delta theta 1. And let me do the following. Let me define a few more things. Let me define a coordinate u, which basically is proportional to the separation between the antennas, but projected in the direction of the source and divided by the wavelength. So I'll call that u, and I'll call delta theta 1 as L1. And I'll have L1, L2, L3 up to Ln. U, of course, is common for all of them because it doesn't depend on n, right? That term x cos theta 0 has no n dependence. So therefore, I will get V tilde will be equal to summation over n, in e raised to the power of minus j 2 pi u ln. And supposing instead of, I've considered that I had n sources, each of which are point sources inside this field of view of mine, which is capital delta theta, right? But instead of assuming that I have this bunch of point sources, supposing I assume there's a continuous distribution of intensity rather than breaking it up into several small points, I say there's a continuous distribution of visibility with angle. If I were to do that, then the summation would get replaced by an integral, and I would get that the measured visibility would be I of L e raised to the power of minus j 2 pi u L dl, and this would obviously be a function of u. Everybody
That's the
agrees?
continuous sources, right?
Now I'm assuming that the distribution is continuous. It's not a collection of discrete point sources. Yeah? Everyone's, yeah, go ahead.
Earlier, the discrete point sources were all at the same angle theta 0.
They were, no, they weren't. They were at angles theta 0 plus delta theta 1, theta 0 plus delta theta 2, and so on, right? This was the collection of sources which I had. One source at delta theta 1, which corresponded to geometric delay tau g1, another at delta theta 2, corresponding to angle to geometric delay tau g2, and so on. And then we worked out that the geometric delay has two components. One, which is a geometric delay towards the pointing center, which is like a reference geometric delay, and then a differential delay for that particular source's location. Right? And that common one for all sources we took out, because we know that common one, it depends on where I pointed the antenna, which I know.
So delta theta would correspond to theta naught plus delta theta by 2, those ones, right?
Those ones, they are lying within the field of view of the telescope. That's why I'm sure that all of them, that all the delta thetas are much less than pi, because they lie within the field of view of the telescope. And so I can integrate over a large angle, a large bandwidth also. There are sources which lie, as you said, within this area, within the field of view of the telescope.
Okay, sir.
Right? So you can see what we did now was two things. One, we allowed ourselves now to have a large bandwidth at any angle. All that I had to do was I had to take the measurement, and instead of working with that measurement itself, I just multiplied by this factor, which I know, which is depends only on the frequency of observation and the angle at which I pointed the telescope. And that allows me now to use a large bandwidth at any angle whatsoever. And if I relax the assumption that I have discrete sources and instead allow them to be continuous, I get this relation. What is this relation called?
The Fourier transform.
It is a Fourier transform. So it tells me that the visibility that I have measured is the Fourier transform of the sky intensity distribution. And we'll pick up from here tomorrow. So I'll pause here. I won't go any further, but I can take a few more questions if there is time.
Sir, this is the visibility, the same thing?
This is called the visibility.
Okay.
It's the output of the correlator, and it's also called the visibility. Right. So you can see it is an interferometer kind of thing. That is, we are taking two waves and making them interfere. But unlike in the double slit experiment, as I said, we've extended it in different directions. One, we allowed more than one source. Two, we had a larger bandwidth. And not just one single frequency, we are integrating over a large number of frequencies.
So since this is a Fourier transform, like how does that help us? What
yeah. So that is what I'd like to get into tomorrow when we talk about imaging.
Okay.
I first just want to establish that what we are measuring has a clear mathematical relationship to what is there in the sky.
Yes.
Sir, is this still all in the same one-dimensional thing?
Yes. So if I were to extend it to 2 dimensions, it's not very hard to do. I will just say that what would happen is that instead of having a u, I would have a u and a v, and that would become integral of I Lm e raised to the power of minus j 2 pi ul plus vm dl dm. That's what happens. And the algebra will take us a little longer to do, but you'll end up with this. And to just give a quick answer to that question about how did this help us, the way it helps us is because the Fourier transform is invertible. If I know the Fourier transform of a function, I can compute the function. So if I measured the Fourier transform of a function, it's as good as knowing the function. I can invert it and get the function back. And so if I were to be able to measure the Fourier transform of the sky, I can get the sky back by doing an inverse Fourier transform.
Okay.
And we'll look at that tomorrow. Yeah.
So what is U?
U is here. This is what I defined over here. U is x cos theta 0 divided by lambda.
Sir, so when you say it is one-dimensional, you mean that it is only function of theta?
It's only a function of theta and not a function of phi.
Oh, okay, sir.
There are no local oscillators in this, like in interferometry system, right?
In a single dish, there are interferometers. I did not get into the details of it. I'm sorry, local oscillators. There are local oscillators. It will make our algebra a little bit more complicated, but it won't change anything fundamental. But yes, there are local oscillators.
Excuse me, sir.
Yeah.
So we have light coming from different sources, right? So how do we make sure that those sources will actually interfere?
They don't. That is the whole point. Sorry, let me just go back. See, what I have done here, I have n sources, right? 1, 2, and going on up to n. And what I did then was I added up their intensities. I can only do that if one source does not interfere with the other source. If one source can interfere and beat with the other source, I will not be able to add up their intensities, right? I'll get cross terms when I multiply the voltages. I'll get the interference of source 1 with the I'll get interference of radiation from source 1 with radiation of source 2. There are no terms over here which involve interference of the wave from source 1 with the wave from source 2. And the reason why there are no such terms is because we have assumed that these sources are independent, they do not interfere. They're not coherent. Does that answer the question?
Yes, sir. Thank you.
Yeah.
Sir, and one question that the dish antenna has this resolution, full width, half maximum thing.
Yes.
So we are not considering that effect and considering only along the axis.
No, we did very much consider that effect. Let me just go back to the start. Where did I do it? It ended up over here, right? So this is that effect, right? That I am receiving radiation not only along the direction to the axis, but at some range of angles around the axis, right? Which that range of angles is lambda by d, right?
Oh, okay,
that's what it's the resolution, but it's also the field of view, which tells me that I don't see any radiation from anything outside these angles. And that is the same thing that I have called delta theta over here.
Oh, okay, sir. Sir, we consider it to be coming from the same angle theta 0 and not a small deviations.
What do you mean by small deviations? See, the telescope will not see sources outside of this area of this angle delta theta 0. And what we assumed was that inside this angle delta theta 0, there are many, many sources. Even inside that small area, there are many, many sources which are at delta theta 1, delta theta 2 up to delta theta n.
Okay, so understood now.
Yeah.
These small deltas are within that.
All of these small deltas are within, they lie within this range. They lie in this range which I have given over here.
Okay, sir.
All right. Yeah,
by tomorrow.
Yeah, I guess maybe we could stop.
Yeah, thanks very much for a very, very lucid and beautiful introduction to the basics of interferometry, Jayaram.